Welcome, everyone. Thank you for joining us today. We're going to take a few minutes to let people join, but in the meantime, please feel free to use the chat to introduce yourself and let us know where you're joining from today. We're getting some good messages from where everyone's coming from this morning. Uh, we're just going to give it one more minute before we get started, and then, so please keep sharing where you're from. Wonderful. Looks like we've pretty well stabilized with the numbers, so we're going to go ahead and get started. Thank you, everybody, for joining us this morning for the NICE Future Initiative webinar titled SMRs and Microreactors, Critical Considerations for Deployment. Just a few housekeeping things before we get started with the content. This webinar is being recorded and will be shared after the session. Upon entering, you will be muted and you will stay muted for the duration, but you can use the chat feature and add your inputs in the Q&A box throughout. If you have any technical issues, please message Sophie Schrader in the chat. And you can adjust your audio through the audio settings, or you can also find the dial-in settings or information in your registration email if there are issues in that direction. Finally, we'll be launching a survey at the end of the event, so please take a few minutes to fill that out at the very end of today's webinar. Your feedback is really important to us and helps improve these sessions in the future. For today's session, I'll provide a quick introduction to our speakers before we dive into the presentations themselves. We'll hear some opening remarks on the NICE Future Initiative and Canada's work on SMRs and microreactors. Then an overview of the work from Idaho National Laboratory on SMRs and microreactor technologies, including US deployment considerations. And finally, we'll hear from Radiant Nuclear on their Kaleidos microreactor and the plans for deployment. To close out, we'll have a brief panel discussion with our speakers, and then, of course, that survey at the very end of this. We're really excited for our mix of speakers today. We'll be joined by Tim Gauthier from Natural Resources Canada, Brian Smith of Idaho National Laboratory, and Phoebe Lind from Radiant Nuclear. And I'll be your moderator today. Max Fanata is my name. Researcher from National Laboratory of the Rockies, working on long-term capacity planning and market structures. And with that, I'm happy to hand it over to our first speaker, Tim Gauthier. Tim is the Deputy Director for Bilateral Relations and Market Access in the Nuclear Energy Division at Natural Resources Canada. In this role, he leads a team that supports Canada's international nuclear energy engagement, including collaboration with partners to advance nuclear exports, market access, and opportunities for Canadian nuclear expertise and technologies abroad. And with that, go for it, Tim.
Thanks, Max, and good morning or good evening to everybody, depending on where you are. As Max said, my name is Tim Gauthier. I'm the Deputy Director of Bilateral Relations and Market Access at the Department of Natural Resources, or Natural Resources Canada, for the Government of Canada. As a co-lead, Canada is a co-lead of Nice Futures. I'm very pleased to be here to provide just very brief remarks and scene set for the fantastic panel and discussions that will be a part of this webinar. And we're really pleased to support this continued work of Nice Futures to create practical spaces for information sharing and collaboration. At its core, Nice Future helps bring together the right mix of governments and experts, industry, other stakeholders to discuss how nuclear energy can contribute to clean energy goals, energy security, and long-term economic development. And that role is especially important for today's topic. Around the world, interest in nuclear energy, including SMRs and microreactors, continue to grow. These technologies are attracting attention not only because of their potential to provide clean electricity, but also because of their possible applications in remote communities, industrial sites, mining operations, and other contexts where reliable, non-emitting energy can be difficult to access. But as everyone here knows, interest alone is not enough to move projects forward. Deployment requires careful consideration and many practical issues. And that is why webinars like this can be very valuable. They allow us to move beyond high-level discussions about potential and focus on the practical considerations that countries, developers, regulators, utilities, and communities really need to work through. They allow countries to learn from one another, which is particularly important as many jurisdictions are facing similar questions around how to prepare for first-of-a-kind or early deployment projects. Now, for Canada's perspective, SMRs and microreactors are an important part of our broader nuclear energy landscape. In Canada, nuclear power has played an essential role in our electricity system for decades. It accounts for nearly 15% of our national electricity supply, and it does so safely, cleanly, and reliably. But the impact goes far beyond power generation. The sector supports good-paying jobs, including engineers, operators, skilled tradespeople, scientists, researchers, and provides a significant economic contribution across the country, as well as with our supply chain supporting many projects abroad and leading many projects abroad. Yet, as impressive as our industry's history is, we do believe that its future is even brighter. That's why nuclear energy figures prominently in the federal government's ambitious plans to build a stronger, more resilient, and prosperous Canada. And this was recently reinforced by my minister, the Minister of Energy and Natural Resources, who announced the development of Canada's first comprehensive nuclear energy strategy just last week. The strategy will set out a federal vision for the sector, developed in collaboration with our provinces, industry, utilities, labor, Indigenous peoples, and other partners. And it is expected to focus on key priorities, including enabling new nuclear builds, positioning Canada as a global nuclear supplier and exporter, strengthening uranium and fuel opportunities, and advancing next-generation nuclear innovation, including SMRs and microreactors. And that last point is especially relevant to today's discussion. As many of you may be aware, the Canadian nuclear industry is at the forefront of SMR deployment, with Canada on track to become the first country in the G7 to deploy a grid-scale SMR. And Canada is also beginning to look more closely at the potential of microreactors for remote and northern applications, where dependable heat and power is essential. And recently, it was announced that the Government of Canada, through the Department of National Defence, is making an initial $40 million investment this year to assess the potential of microreactors that could provide heat and electricity to remote and northern military facilities and operations. In the longer term, this work has the potential to de-risk microreactor technology for broader civilian use, such as remote communities and other industrial sites looking for clean, dependable power. In closing, for Canada, participation in Nice Future is one way we can support a broader international conversation. Canada values the opportunity to work with its partners to share experience, learn from others, and support practical discussions on the deployment of innovative nuclear technologies. And today's webinar is a good example of collaboration in action. We are fortunate to have speakers who will bring perspectives on SMR and microreactor technologies, market considerations, deployment pathways, and emerging opportunities. And with that, I just want to thank again all the organizers and the speakers and participants for joining today. And I look forward to hearing the discussion, and I'll pass it back to Max. Thanks so much.
Thank you so much, Tim. I'm happy to introduce a speaker who was not on that previous slide, Alicia Duncan, who is serving as the Deputy Assistant Secretary for International Cooperation in the U.S. Department of Energy's Office of Nuclear Energy. With a background in international nuclear energy policy, she has served in various roles at the Department of Energy, managing bilateral and multilateral relations. Internationally, Ms. Duncan held posts in France in France with the OECD Nuclear Energy Agency and in Japan as the energy attaché at the US Embassy in Tokyo. Thank you so much, Alicia.
Thank you, Max, and thank you also to Holly, Jal, and Anusha for organizing yet another webinar in the series that we have this year. I'm excited about the attendance for this one because you all continue to come join us as we have these important conversations. I also want to thank our speakers that are rock stars in their own right. What a great conversation to be having about small modular reactors. And I appreciate that Tim joined us this morning from NRCan to provide Canada's perspective. The U.S. is indeed excited about the Canada project because it does feature the BWRX 300, which is the GE Vernova technology. So we are off to yet another instance of what great collaboration looks like, what the future of SMRs looks like. And you all are here to join us and hopefully stay engaged in the chat. I see that there are a lot of countries that have joined us, a lot of companies that have joined us, and we are excited to be with you yet again today. This conversation with those speakers that we have lined up for you is undoubtedly going to have you pondering some things. I want you to make sure that you put your questions in the chat. I want you to make sure that you are engaged. And I want you to use this conversation as an opportunity to take information back to your capital, to your colleagues, to those who are curious about nuclear, because we are the ambassadors for nuclear. So if you did not know you were an ambassador, let it be so today. We're the ambassadors for nuclear, and whether you are in, I saw Lithuania, I saw Austria, I saw quite a few folks from around the world. No matter where you're joining us, nuclear is an important conversation. Recognizing that each country is going to make their own choice about what they do with the deployment of nuclear, it is still critically important that we're all aware because there's so many non-electric applications around nuclear that SMRs and micros bring to bear, that we want to make sure that you're not just thinking about nuclear as a power source. So please listen with us today, be engaged in the conversation, and we are excited to bring you this session from Nice Future. I'll turn it back to you, Max.
Thank you so much. That was wonderful, Alicia. I'm happy to introduce our next speaker moving forward, Brian Smith. Brian is the Acting Chief Technology Officer of Nuclear Science and Technology at Idaho National Laboratory, where he leads the laboratory's efforts to accelerate the deployment of advanced nuclear reactor technologies. Brian brings over 25 years of US government experience in commercial nuclear technology and policy to his position. All right, for Brian.
Great, thank you so much, Max, and thanks to our opening speakers, Tim and Alicia. It's just a pleasure and an honor to be invited to come into this collaboration, this group of ambassadors. I love how you said that, Alicia. To have this conversation, as I saw folks put their names and affiliations in the chat, I saw a lot of friends and colleagues, folks who I hold up as mentors in this space. What a great opportunity to come and have this conversation. Let's see, I'm going to share a few slides here, and just to kind of walk through some things. I don't share slides or use slides when I give a talk just for the sake of using something. I prefer to use a slide if it actually helps drive the conversation forward. And I'll hit on a couple of topics where I think some visuals are helpful. First of all, just to kind of kick us off, and I'll note, this overview I'm going to give is, I'll admit it is fairly U.S. centric. A couple of things. Number one, I come from the U.S. Department of Energy owned Idaho National Laboratory, and so there is certainly the U.S. is a hotbed of activity for nuclear. And Idaho National Laboratory is the lead laboratory for nuclear energy research, development, and demonstration. So you can imagine, especially in the last couple of years, there's been such focus on developing and deploying advanced nuclear technologies in the US. And so while my presentation may be somewhat US focused, I always remind myself, and I think it's important to call out here, I think what I'm laying out is sort of a roadmap of opportunity for all of our partners and friends around the world who seek to deploy advanced nuclear technologies. It's an exciting time for everybody, and so I'll talk about what's going on in the U.S. First of all, this chart that I've got up, some interesting historical context. The light colors kind of show the global nuclear capacity. The darker colors are focus on the U.S. But it is kind of interesting to see where we've been and where we're headed. And it's where we're headed. It's the green bars to the right of this chart that present to me the opportunity and also at the same time keep me awake at night, right? Because we have some very ambitious targets both worldwide for tripling nuclear capacity around the world by 2050, and within the United States, which our current target is to quadruple nuclear capacity in the United States by 2050. So that's going to require a substantial amount of new nuclear capacity. And I think it's good for us to look at what embracing that opportunity can look like. But we need to remain mindful of those choke points, those areas of risk to achieving this ambition. And those are some things that we can flesh out when we do the panel discussion later. I'll touch on some of them though in this overview. First of all, I'm going to hit on just a few key milestones from the last couple of years in the world of large-scale nuclear. And I recognize here in this engagement, we're here to talk about small modular reactors, microreactors. But one thing that is interesting, I'd say even in the last 12 months or so, there is, large-scale nuclear, which had sort of fallen by the wayside in many of the conversations. It's kind of back in the conversation, not necessarily overtaking the talk of SMRs and micros, but given load growth projections, and I'll just focus, say, in the United States, load growth projections really are representative of the way it looks around the rest of the world, large part driven by data center growth, the growth of artificial intelligence and everything that can be done by leveraging various AI tools. That's driving a lot of that load growth. It's not only data centers, obviously electric vehicles and industrial processes are driving load growth. But with such substantial load growth projections in every country around the world, large-scale nuclear, and think nuclear power plants producing upwards of 1,000 megawatts or more. Those are kind of back in vogue as part of an overarching nuclear strategy, certainly in the United States, and I think it's fair to say in other countries around the world. And so most recently in the US was for large-scale nuclear, the deployments at the Vogtle plant in the US state of Georgia. Those are online, producing clean, reliable economic power. And I hold that up certainly to my U.S. audiences. I hold that up as a win for showing we can still deliver large-scale nuclear in the United States. Frankly, there are other countries in this world that are doing it in a more serial fashion, and we in the U.S. have a lot to learn from those friends around the world. But we can do it in the U.S., and there's more to be done. I'll talk about some more of that in a moment. I want to turn to this now was a couple years ago, but restarting a shutdown large-scale nuclear power plant, that's a big deal. And that's not something that we were talking about. I would submit, and again, we can unpack this some more during the panel discussion, but I would submit that November of 2022, when ChatGPT was introduced to the world, that really set off these substantially revised load growth projections that were just shooting upward. And one of the plants in the U.S., 3 Mile Island Unit 1, had been shut down by Constellation in 2019, based only on economics. They just didn't see that it was economically viable to keep it running. Now post ChatGPT, post AI, kind of revolution and whatnot, Microsoft comes along and approaches Constellation and says, "Hey, if we do a power purchase agreement and we agree on a certain rate of electricity that we'll buy from you for the long term, would you turn that plant back on?" And Constellation ran the numbers and said, "Yeah, we sure would." What a difference a few years and some technological advancements makes, that a plant shut down in 2019 turns back on here in the next couple of years because of the involvement of one of those hyperscalers. Very interesting. Another restart in the U.S. is happening in the U.S. state of Michigan at the Palisades plant. And that is being supported by the Department of Energy, their Office of Energy Dominance Financing, which presents some great financial tools for anyone involved in nuclear. And so this is just a great win and shows what a government partnership can achieve in turning back on a plant in the U.S. And then again, just in the world of large-scale nuclear, the Westinghouse technology, the AP1000 large-scale nuclear reactors. There's an ongoing discussion among several entities to get to work deploying more large-scale nuclear reactors. We often say in the U.S., those Vogtle plants that I talked about at the top. Yes, we built and deployed Vogtle 3 and Vogtle 4. We've got to get on to building the next one. We have a real opportunity to seize that cost and schedule curve, those curves that drive downward, lower costs and faster schedules to deploy large-scale nuclear, and that's what that's all about. So with that piece of the discussion, kind of setting it aside, let's talk about what's coming in the area of SMRs and micros. I love this chart, and essentially I could give a talk like this by using only this chart. There is so much happening across the landscape. Lots happening at Idaho National Laboratory. And so this offers a timeline of demonstration reactors, some reactors that are first of a kind, but intended for commercial deployments with the first of a kind. But if you start here on the left in 2026, in fact, this chart was recently, we had to redo it. We used to have individual icons all across the timeline. Got to the point where you couldn't fit any more of these icons on the chart. So we had to reformat it just to load it up with all of the activity, all of the various reactor developers that we're partnered with, both in Idaho and around the country. to deploy. So it's an exciting time. I'm so glad we've got Radiant as part of this discussion today. They've been a close partner with the Department of Energy and out at INL for years. And Radiant is currently moving into one of our test beds that's depicted in the bottom left of the chart, the DOME test bed. That's the demonstration of microreactor experiments. That's a test bed Idaho National Laboratory has deployed. As I mentioned, Radiant is moving in, and Radiant is going to turn on their microreactor experiment, their Kaleidos test reactor here this year. That's going to be an exciting win, I think, across the advanced nuclear landscape. Lots of other important partners doing great work there. ALO, Antares, Deployable Energy, you see there. Just lots happening in Idaho, as I mentioned. There are other states where, as I mentioned, those first-of-a-kind deployments are taking place. So I don't necessarily need to go through the entire scope here, but just know that in terms of demonstration reactors, lots of activity. We're no longer looking at things on paper and saying, won't it be nice when that thing gets built, or won't it be nice when that thing turns on? If you swing by Idaho National Lab or some of these other places depicted on the chart, you'll actually be able to witness an advanced reactor, turning on before your very eyes. So that's exciting. Now, as I often say, and again, we can unpack some more of this during the panel, demonstration reactors don't mean, commercialized fleets of commercialized advanced reactors around the country and around the world. So lots more to do, and frankly, an exciting time for folks at the laboratory and throughout the nuclear industry to work through the workforce challenges that we're going to have, the supply chain challenges, figuring out how to make sure that the fuel needed to fuel these reactors and fleets of these reactors is available. Again, exciting opportunities. One thing I want to highlight is an announcement the Department of Energy made just in recent weeks, and that's the nuclear energy launch pad. So with what I described as far as this sort of demonstration ecosystem for advanced nuclear, a lot of that was spearheaded by what was called the Reactor Pilot Program and the Fuel Line Pilot Program. Both programs that the Department of Energy rolled out last year, spurred by an executive order, a series of executive orders that I'll talk about, signed by the president last year. And the Reactor Pilot Program, Fuel Line Pilot Program stimulated a lot of interest from the industry. They said, yes, I want to get in on that. I want the Department of Energy's support to prove to the investment community and the off-takers that this is achievable. I can build real things and operate real things. The Reactor Pilot Program, Fuel Line Pilot Program were kind of a one and done, though. They were intended to get right at the executive order direction. So the nuclear energy launch pad essentially establishes an enduring, we'll call it reactor pilot program, but it's an enduring presence, an institutionalized way for advanced reactor developers to continue coming to the Department of Energy and Idaho National Laboratory, the rest of the laboratory system, and find ways to deploy their reactors. There are a number of new companies that have started since the reactor pilot program got underway. So those companies are the ones we're talking to today to come into the launch pad. And under the launch pad, and you can go off and read more about it. It's a very cool concept, but you have Launchpad INL, which means you can target your demonstration reactor at the laboratory. You also have Launchpad USA. We're working with the National Reactor Innovation Center, or NRIC, at INL. You can build your demonstration reactor outside of INL. You could do it on a university campus, for example, which is exactly the model being used by one of the first Launchpad partners that was announced last week. So exciting times for demonstration reactors and the advanced nuclear landscape to drive the mission forward. I mentioned those executive orders. I don't want to take too much time here because I know we're kind of moving through a program, and frankly, we're going to have a lot of time during the panel to unpack some things. I'll just quickly hit on 4 executive orders that were signed last May, in May of 2025. Reinvigorating the nuclear industrial base. I'll draw your attention on this slide to that middle bullet of restarting, completing, and uprating nuclear plants. 5 gigawatts of uprates. That's an exciting opportunity, as I think a lot of folks on here know, especially with the operating reactor fleet that we've got today. In the US, we've got 94 reactors. But take your reactors around the world, there are ways to get more power out of those reactors. When you go through that process, it's called an uprate. In the US, the Nuclear Regulatory Commission authorizes, signs off on approving those uprates. And there's a goal to find 5 gigawatts of uprates in the operating US fleet by 2030. The Department of Energy announced a program called Uprise recently, intended to get at that. Getting 10 new large reactors to start construction by 2030. Again, exciting opportunity for large-scale nuclear. So I just wanted to call that out. The nuclear workforce, growing that, scaling it so that we can scale to our nuclear ambitions. That's also included in this. Reforming nuclear reactor testing at DOE, that is, I mentioned the reactor pilot program. That was specifically intended to get at this, and the nuclear energy launch pad is a way to keep it going. So I won't dwell on this one too much. That is a picture of the dome, the demonstration of microreactor experiments that I mentioned Radiant is currently moving into. Deploying advanced nuclear technologies for national security. I'll just say, it's perhaps not surprising that within the United States, the Department of War has military installations all around the country and actually all around the world as it contemplates ways to power those military installations. It's not surprising that they would say, gee, nuclear seems like an exquisite way to provide reliable baseload power. And so the Department of Energy is engaged, with the Pentagon in the U.S. and Idaho National Laboratory is happy to help on that. International engagement is also captured in here, at least 20 123 agreements here in the coming years to enable the export of U.S. nuclear technologies. Really a great opportunity for the U.S. to continue to partner around the world. And finally, reforming the NRC. I mentioned the Nuclear Regulatory Commission in the U.S. For 70 years, the NRC essentially, in terms of power reactors, they were regulating one type of reactor, light water reactors in the U.S. So as the focus has shifted to small modular and micro reactors, using coolants and moderators that are not light water, the regulatory framework needed to evolve. There was some legislation out of the U.S. Congress in recent years to direct the NRC to do that. And this executive order from last May sort of put fuel on that fire to move the NRC quickly to look at its regulatory framework and find ways to make it more efficient and essentially more inclusive of these advanced reactor technologies. Good news there. And again, in terms of seeing real action, we're not just looking at evolving regulatory framework on paper. We're seeing the NRC deliver time and again on milestones, issuing construction permits for advanced reactors. This is an exciting time at the NRC and the regulatory framework to achieve these ambitions. So with that, I'd like to bring my prepared comments to a close. I'll hand it off to Max. I'm going to stop sharing my screen here and can't wait to continue the dialogue as part of this discussion. Thank you.
Thank you so much, Brian. That was wonderful. And so with that, we're going to move on to our final speaker of the day, Phoebe Lind. Phoebe is a government affairs associate at Radiant Nuclear, where she works to bring Radiant's microreactor technologies online in the United States. She has a passion for transforming the energy sector through the deployment of advanced nuclear technologies. With that, Phoebe, I'll hand it over to you.
Thank you so much, Max. Thank you so much to Nice Future for hosting this webinar and having me here. Also, I couldn't ask for a better presentation ahead of my own from Brian. I think that set the stage really well for the context, both within the industry at large, but also all of these government programs that I think Radiant is involved with almost every single one of the ones that Brian mentioned. So a great setup for us. But yeah, as Max mentioned, my name is Phoebe Lind. I work on the government affairs team at Radiant Nuclear. Radiant is a microreactor developer. We're building the Kaleidos reactor, which is a 1 megawatt electric high temperature gas reactor. I also have some slides to share, so I will pull those up now. Okay, I think we should be good to go. But yeah, again, as Brian was talking about this pathway to opportunity before I jump into everything that Radiant is doing, I do want to recognize the groundwork that the Department of Energy and national labs have laid for developers like Radiant. Not only are we leveraging like the existing infrastructure at Idaho National Lab in Dome, as Brian mentioned, but our success in 2026 and beyond is absolutely due to like the years of advanced reactor development and the expertise in the labs. So we're very lucky to be a part of this movement. Here's a little bit about Radiant. So our headquarters is in El Segundo, California, which is just south of LAX in Los Angeles. This is where we are building our very first reactor that is in the final stages of assembly that will be shipping out to Idaho shortly. All of our engineering and operations happens out of LA. That said, we are also rapidly expanding across the country. We've got our HQ in LA. We have an office in DC, which is where I am located. We'll be deploying at Idaho National Lab. We recently announced in fall of 2025 that we are opening our factory, which you can see, I've got a little blurb right there, but it'll be a 350,000 square foot facility that'll be in Oak Ridge, Tennessee. That's really critical to being able to mass produce microreactors at scale. So we're now in California, Idaho, DC, Tennessee. And just 2 weeks ago, we announced that we have been paired with Buckley Space Force Base in Colorado to deploy a microreactor to the Space Force Base there. So now expanding to Colorado as well. We've got a really fantastic team at Radiant. A number of engineers have come from places like SpaceX, Naval Reactors, even pulling from the national labs themselves. We're at over 150 people now, but again, rapidly expanding in LA and across the country. We are primarily privately backed, so our recent raise will support our commercialization efforts over the next couple of years as we deploy in Dome and as we look forward to our first commercial project. Dome is really critical to that, but it's certainly, we've got ambitious goals beyond that as well. We are building the Kaleidos reactor. My boss likes to call this a megawatt in a box. So it's 1 megawatt electric, so it's super tiny compared to the large scale or even the SMRs that we're often talking about these days. But we have a number of benefits from going this small that makes it a really great solution for the power needs of our customers. So first of all, our main goal was that we wanted something that was portable. You'll see in some of the later slides, we have a few other renderings of what this would look like, but it can be shipped by land on the back of a semi-truck, by sea, by air even on a C-17. But the importance of this is that it is portable all over the country, all over the world, and you can deliver that quickly. So you're looking at days or weeks of installation rather than years for, traditional large-scale nuclear projects. This image here is an example of what a 4 megawatt installation would look like. I don't know if you can see my mouse, but each of these white boxes represents one unit, one reactor. This is concrete shielding that would surround each reactor unit. But essentially you can have, 1 megawatt all the way up to 10 or more even, depending on the power needs of that customer. But this is intended to be an on-site, potentially behind the meter solution for our customers. One interesting thing about microreactors that we tend to get a lot of questions on is because this is built in a factory, we ship it to site. However, our reactors don't stay on site after they have completed their useful life. We operate on 5-year refueling cycles where after 5 years, that unit gets shipped back to the factory, we refuel it and send it out for another deployment. The total life cycle is 20 years, but after that 20-year cycle, that unit is ultimately returned to the factory, decommissioned there, and all of the spent fuel is stored at our factory in Tennessee. So there is no on-site waste that stays at our customer site. A good way to think about this for context of like similar energy resources is that it's like a diesel generator. This could be a one-to-one replacement for a diesel generator. That said, like all other nuclear resources, it's clean energy. So if you were have a microreactor, on site at your installation instead of a diesel generator, you would be avoiding almost 650,000 tons of carbon dioxide pollution over that 20-year reactor life. So we know the environmental benefits, the air quality benefits of not having that additional fossil pollution in your backyard would be a really great opportunity. The first question we tend to get after what is a microreactor is, what are the applications for microreactors? Again, it's super small and a very different use case than large-scale nuclear. That said, we've got a wide range of applications for both commercial and government customers across the board. For commercial applications like SMRs, you're seeing a lot of interest from data centers. Radiant has a contract with a hyperscaler called Equinix, for example, to deliver up to 20 reactors across the country. So having that resilient power on site, especially as they are battling for power needs with communities, it's both helpful to that customer and to the communities to have that power on site, off grid. But we're also seeing interest from remote operations like mining and oil and gas. I know there's been increased interest in opportunities in like the Permian Basin, for instance, for microreactors to support oil and gas operations out there. But you can also see some novel applications for microreactors, so transportation infrastructure, like electric vehicle charging. If you had 100 cars charging at once, that's going to be a pretty big strain on the grid at like a massive EV charging station. So in places where that transportation electrification is expanding rapidly, this could be a really great opportunity to plop this down and provide that on-site power. Across the board, though, including both our commercial and government customers, the commonality that you're seeing is that these are folks who need resilient on-site power. This is powering critical infrastructure that cannot lose power if the grid were to go down. So for things like military installations, hospitals, even university like microgrids, a microreactor can be a really great one-to-one fit depending on their power needs. Again, from like 1 megawatt all the way up to 10 or more. That said, if you're going like 20 plus, maybe we'd refer you to some of our other competitors in the industry who have a better fit for your particular power needs. But as Brian mentioned too, we've been working with DOE and the national labs for many years. We've been very lucky to have such supportive government partners as we've been developing this technology. This is just a sampling of some of the things that we've been involved with over the years as we've really been able to incrementally make progress on our initial reactors design many years ago to modeling what resilient energy microreactors can provide for military installations, and then ultimately to the projects which I'm excited to share with you today, which are our reactor deployments at Idaho National Lab, and then with the DoD at Buckley Space Force Base. So as Brian mentioned, we've got some images here. DOME, in addition to being a really great acronym for demonstration of microreactor experiments, it is literally just a big dome. As I mentioned, our reactor is currently underway in its like final stages of assembly, and that is happening at our headquarters in LA. We have some other infrastructure that we're moving into the dome currently, but the reactor itself will be shipped out in just a few weeks from LA to Idaho. It'll then be fueled at Idaho National Lab, and we'll be doing full power testing beginning this summer and through 2027. So we're really excited about the fact that this is not just a criticality test. We will be getting a lot more information, a lot more data that is going to support the deployment of our commercial reactors, as well as support all of our licensing efforts with the NRC. For DOME, this is going to be something that is a DOE authorization. Back in February of 2026, DOE approved our PDSA, that's our preliminary documented safety analysis for the Kaleidos development unit that will be going into DOME. That represents about 2/3 of our nuclear safety documentation required for our DOE authorization. And then we're currently finalizing our DSA, which is that third step required to actually turn on our reactor once we get to dome. Importantly, as we're talking about all of these different demonstration opportunities, our end goal is commercialization. We're very excited about the fact that military applications are a first mover customer for us, and we've been engaged with ANPI, or the Advanced Nuclear Power for Installations program. That is something that is run by the Defense Innovation Unit, and we've been engaged with the Air Force for a number of years on that program. The Defense Innovation Unit is also what you may be familiar with, the Army's Janus program. That also falls under DIU, and we've been participating in that opportunity as well. We're excited to hopefully have some news about that in the coming weeks. But for the meantime, also very excited to talk about our Air Force news. They paired up 3 different developers with different Air Force bases across the US, depending on the power needs and those timelines to deliver. We're very excited to be going to Colorado. And again, as we were talking about those executive orders earlier, these 2 projects are really great examples of some of the real projects that those executive orders have been able to accelerate. We've got some very ambitious deadlines. That July 4th, 2026 deadline to go critical is coming up very quickly, and it's all hands on deck to meet that goal. And then the executive order on nuclear power for national security, that set a goal of September 2028 to have a microreactor on a military installation. And we are on track to meet that goal as well. Looking ahead to be able to enable all of these projects, Radiant also is building our microreactor factory out in Oak Ridge, Tennessee. This will be both our microreactor factory will actually be manufacturing all of these, but also a fueling facility. We recently submitted our Part 70 license application to the NRC, and that was accepted by the NRC just a few days ago. So very excited to see the quick progress on that. We've got some really incredible partners on the regulatory side of things, including DOE, including DOW and the NRC. And it's really great to see all of these different groups working together as we're deploying reactors, across all of these different programs. But ultimately looking at, full-scale commercialization, this reactor factory will be really important to enabling that. Our goal is to scale up to a production of 50 reactors annually, so that's about 1 reactor a week. We did break ground on this facility just a few weeks ago, and we will plan to have that fueling facility up and running by the end of this year. The actual reactor factory will probably open in 2028 is our current goal for that, where we'll actually be able to start deploying reactors from that factory. In the meantime, our first couple of reactors will be built from our LA HQ, and then fueled at our facility in Oak Ridge. We've been very happy to receive a very warm welcome from the Oak Ridge community. Again, strong national lab presence there with Oak Ridge National Lab, and a lot of other really great partners in the area. The nuclear community is so strong there, and we've really been able to see the benefit of that as a new resident. Also relevant just down the road from us in Oak Ridge is our fuel fabricator for Dome, for a reactor that is going into Dome, Standard Nuclear. And being able to work so closely with them, again, being in the same community, has been very, very helpful. This goes into a little bit more detail about the life cycle of Kaleidos, again, with our unique approach to factory fabrication and deployment. I think this helps illustrate what that life cycle looks like. So as I mentioned, it's all assembled under one roof in our factory. We deliver that to our customer site. We plug it into our operational shielding. These are big modular concrete blocks that get dropped in, but it's very minimal on-site construction. Those run for 5 years at a time. They're refueled every 5 years, and then the total life cycle, again, is 20 years. So here, run for 5 years, refueled, sent back out. And then ultimately, after 20 years, it's returned to the factory. That infrastructure from the customer site is removed, and you have no spent fuel and no reactor remaining behind at that customer site. everything is stored and decommissioned at Oak Ridge. And then finally, here's a couple of examples of what these reactor deployments would look like in real life. This is an example of like a 2 MW installation at a data center, for instance. Here you would have a pretty small fence line that's necessary for, such a small reactor, which is great because it offers additional co-location opportunities for electricity, or in the future for heat generation, for cogeneration opportunities as well. Being able to use that excess heat as a high temperature gas reactor, we can reach temperatures that are needed for industrial operations, all the way up to 700 degrees Celsius. So that's an exciting opportunity that we're looking forward to, microreactors being able to open up new applications, new opportunities. You can power remote mining operations. We were talking a little bit about, remote communities in northern Canada, for instance, in Alaska, that are paying very high prices for diesel fuel. Being able to drop these in areas where the grid cannot quite access is another great opportunity to, bring down energy costs in the long term for both industry and for communities. And here's another example of what that reactor would look like as it's being installed into an operational facility, but being able to provide that resilient power to military installations, again, is one of these first mover customers that we're really excited about. And that is all I have for you today. Again, if folks have additional questions, looking forward to the moderated Q&A that is coming up. But here's my email as well. Please feel free to reach out if you're interested in talking about microreactors. It is very much a personal passion of mine, and I'm excited to see the progress that we're making in 2026 and beyond. So thank you very much, and I'll pass it back to Max.
Thank you, Phoebe. That was wonderful. And thank you to all of our speakers for their presentations. Yeah, we're going to just move on to the panel discussion now today. And I just want to start the panel discussion with, we heard a lot about the potentials, the pathways, and where we're going with all of this work. Maybe starting with Phoebe, radiant focus potentially. What are the biggest engineering innovations needed before these microreactors can be widely deployed?
Yeah, absolutely. I would say it's less of an engineering innovation that's needed and more of a supply chain innovation that is needed. I don't think I touched on this in my presentation, but as an advanced reactor, we are using HALEU fuel. In particular, we are using an advanced fuel form known as TRISO. That said, the fuel supply chain for this really does not exist in the US quite yet. We've got a great partner at Standard Nuclear that is they're fabricating our TRISO for the reactor that will be going into Dome. But again, they're just one group. We've got less than 5 in the US that can produce this fuel that's needed in order to scale. So if we're looking at, widely deploying this in the US and beyond, having that robust supply chain is like an existential issue for advanced reactors. And I mean, even as a microreactor at 1 MW, we don't need that much. When you're looking at a 300 MW installation or beyond, you're going to need a lot more fuel. That said, DOE has also put a lot of money forward to be able to set up this supply chain. I know the Centrus is expanding in Ohio, and we've seen a lot of great success there. I'm sure Brian or Alicia could also talk to that work that DOE is doing in more detail. But when we're talking about like step one, being able to deploy widely, being able to fuel the reactors before we ship them out is issue number one.
Wonderful point. I appreciate that. And I guess moving on to Brian to answer a similar question, maybe could you give an overview of some of these engineering innovations, microreactors, and SMRs across types, and maybe highlight how those change across the different types of technologies?
Yeah, sure. First of all, I just want to say how much I enjoyed Phoebe's presentation. I just, again, I mentioned Radiant is an important partner in this space, and just love to hear that perspective. And I want to applaud the answer on the engineering piece and kind of pivoting more to the supply chain and fuel, because I think that's spot on. And as I take your question, Max, I often tell people, the world of advanced nuclear is it's splitting the atom, which we've known how to do for a long, long time, and like we know how to do that really well. And so advanced nuclear technologies and some of these smaller packages for nuclear reactors. I mean, I come from the nuclear Navy. I started my career in the U.S. government in uniform in the Navy. Right, and I don't like saying what's on a submarine is a small modular reactor. It's its own special animal, but they are small reactors, right? And they're made to fit inside a particular physical space envelope. And so, we've known how to do this, and we've known how to do it quite well. And I talked before about some of these non-light water reactor technologies. So, take for example, the radiant design is gas. It's using helium, right, to as the coolant. You've got with the molten salt reactors that can operate, at lower pressures and really can carry a lot of heat away from the reactor. Right. I mean, just to back up a second, I know not everybody on the on in this session today is really deeply entrenched in nuclear, but when you split the atom, that creates heat, right? And you carry the heat away from the reaction and you put that heat to good use. Water works pretty well for that, but you can use gas like helium. You can use molten salts. You can use liquid metals. That chart that I put up included a number of reactor developers that are using sodium as the coolant. So there are, various other ways to move heat away from the reaction. And what I always like to point out is helium reactors, molten salt reactors. We've done this in the U.S., certainly within the national laboratory system. This isn't newfangled technology where, for example, when Radiant turns on, their reactor experiment in the dome this year at INL, it's not like we're all going to sit around and say, what's going to happen when this turns on and the helium is big, but we understand the physics. Really, what we need to do, what the Department of Energy is leading on, and what the national laboratories are supporting the Department of Energy in, is demonstrating, really it's to investors, that these reactors work, that these reactors are viable. And so the investor community can invest in those exciting opportunities to power whatever it is, data centers, utilities, whatever it is. Or as Alicia mentioned at the top, it's not just about power, it's providing heat. Right? High temperature gas reactors are wonderful for process heat. And in fact, one of the demonstration projects that Department of Energy is partnered on is the X-energy reactor being deployed in Texas, and that's in partnership with Dow Chemical to use the heat from X-energy's high temperature gas reactor. So by using coolants other than water, as we talked about, you do open the use cases for process heat, district heating, industrial heat, electrolysis. You can desalinate water, provide swimming pools of in fact, I was on a panel with Doug Bernauer, the CEO of Radiant, and I told the group, I said, look, with a couple of Doug's reactors, you set that up on a coastal area that doesn't have a reliable source of fresh water. A couple of Doug's Radiant reactors will create Olympic-sized swimming pools, multiples of them every day of fresh water. Right? That's an exciting opportunity, an exciting use case, and something that people around the world could really get into. The opportunities to do that with a standard light water reactor, maybe not so much, but with a high temperature gas reactor, there's a great opportunity. A small one that can deploy fairly easily on site. That's great too, right? So those smaller designs and the opportunities to site in places where you can't site large scale reactors. That kind of creates so many opportunities and wind in the sails for various types of nuclear technologies.
Amazing. Thank you both. It's exciting to hear the engineering maturity of these technologies and how you're thinking about developing them on the large or deploying and developing them on the large scale. Could you talk a little bit about the timelines? Like, what does a realistic timeline for the deployment of these technologies look like? And when we'll see them commercially available to these wide-ranging industries that you're discussing?
Yeah, you want me to I could
We can start with you, Brian, and then we'll move to you.
Okay.
How's that sound?
Great. No, that sounds great because I'll just kind of give a quick overview. You know, let's go back a couple of years. We'll go back a few years to the start of a program the U.S. Congress authorized and funded, and the Department of Energy was in charge of executing, and that's the Advanced Reactor Demonstration Program, or ARDP. The ARDP was devised and sort of came about in the year 2020 with an eye toward demonstrating or deploying these first demonstration reactors as soon as the early 2030s. And the two kind of leading reactor designs at that time, as ARDP was structured, was the TerraPower reactor, that is currently being deployed and it has a construction permit to deploy in Southwest Wyoming. And then the other demonstration reactor in ARDP is the X-energy reactor that I mentioned being deployed in Texas. So both of those were thought of as beginning commercial operations in the early 2030s. And they're still hewing to those schedules today. But I will tell you, a lot has happened since 2020. And so, you know, today I'd be hard pressed to say it's not going to be until the 2030s that we have the first, you know, commercial deployment. I think it's going to be this decade. Now, again, I want to go back to the exciting things that are occurring in terms of demonstrating reactor technologies, turning on reactors under a Department of Energy authorized framework. It's kind of a corollary to what the NRC has for commercial operations. The Department of Energy can regulate these first of a kind demonstration reactors. Now, X-energy and TerraPower are both moving through the NRC process. But with everything going on and what I showed on that chart for these first of a kind reactors coming online, I think the foot or the pedal is to the metal, I will say, in driving forward. I think we'll see those first commercial deployments this decade. I think back to Phoebe's very good point, and as I always like to remind people, one commercial deployment, we're all going to celebrate, right? And we should probably take a day off to do the celebration. But what's really important is scaling. I want Radiant to deploy their first commercial reactor. I want TerraPower and X-energy and so many of these partners to deploy. But what I really want to see is a deployment of a fleet of 10 of a single design reactor, right? That's when we know we're really starting to turn the tide on supply chain and workforce and fuel availability.
I'll provide the Radiant perspective on that as well. I think when people think about timeline, especially looking at that beautiful timeline from INL and all the different projects that are happening in the US, it's super exciting, but it is closer than folks realize. And we will have this demonstration at Dome this year. I think I saw a question in the chat too asking about you know, do we have a test reactor yet? That is our test reactor at Dome. So this will be our first time we're turning on, you know, a full-scale Radiant reactor. And then our first commercial deployment will be as early as like late 2027, early 2028, which is like less than 2 years away. So like the moment is here. That said, especially when we're talking about policy surrounding microreactors, surrounding supply chain, like these issues are, we're going to start running into these roadblocks soon, especially on supply chain. Right now, when we're looking at our Radiant supply chain, for example, like we can source enough of what we need for one reactor, maybe up to 5 reactors. But you know, next year, after we turn on Dome, after we have that first commercial deployment, if we're calling up our suppliers and say, hey, we need 10x of these to build the next 10 reactors. And in 5 years, we're calling them up and saying, hey, we need 50 times as much to be able to deploy 50 reactors. we want to make sure that our supply chain does have the capacity to support that. And then, you can apply that same problem to licensing, making sure that, we can take the progress we're making with DOE now, through like our DOE authorization, applying that to our NRC license that we'll need for our commercial reactors. But then when we're trying to deploy 50 reactors, making sure that the NRC is really well set up, they have enough staffing, they have the capability to be able to, license 50 reactors across the US. And that's not just for Radiant, but for all of these advanced reactors that are going to be deploying, distributed nuclear across the country. So making sure that we're ready, for these first ones in the next year or two, and then scaling. I think there's a lot of really great organizations, outside of the government, outside of industry too, like the Nuclear Scaling Initiative, like Clean Air Task Force are starting to talk about these issues about, how can we take the really great progress that is being accelerated by the executive orders from 2025 and making sure that that is leading to long-term sustainable progress. And we have a really robust industry to be able to make sure that we're carrying all of this momentum forward.
Amazing. Thank you both for that. So thinking about this somewhat paradigm shifting supply chain question, the manufacturing side of this, and how it's such a shift potentially in the way we look at this technology, could you both discuss a little bit about the core considerations when you're, in a way, optimizing SMR or microreactors for factory fabrication versus on-site, and maybe discuss some of those potentials or challenges? You've already mentioned supply chain as a key limitation in this, but maybe dive deeper into some of those implications.
Yeah, I can again provide the Radiant example really quickly, and then I'm sure Brian will be able to provide more info about all of these other fantastic technologies that are taking off. I think one thing that is super interesting about how Radiant came to be, I'll give like a super brief history lesson. So our CEO, Doug Bernauer, he was a former SpaceX engineer. While he was at SpaceX, he was looking at a really interesting problem, which was how would we power a colony on Mars? Because that's the type of thing that they talk about at SpaceX. But ultimately, the answer that he came to was nuclear power. But as he was like looking around the marketplace, a microreactor or something that could deploy that kind of power density, but in a smaller container, didn't really exist. And then in like 2019, 2020, Project Pele came out. So that was the first time that we saw, that demand for, a small commercialized nuclear microreactor. Ultimately, that was what inspired Doug to spin out Radiant from his work at SpaceX. But when he was designing this reactor, it was designed with like a defense customer in mind. It needed to be portable. It needed to be shippable on a C-17. So those constraints inherently required our engineers to be really creative about, okay, you can't go over, 75,000 pounds because that is like the weight limit to be able to transport this by air. So, those constraints required creativity at the outset. And then as you're looking to mass manufacture that in a factory setting, we're looking at how can we develop production lines. So it's not a construction project, which means the construction that is happening on the ground, it's not really construction, it's like site work. So maybe you're doing some grading, you're putting up a fence line, but you want to make sure that when you are deploying this product, it is as minimally invasive as possible to that site so that when you need a microreactor, let's say in the future, we need a microreactor on Guam and they've got 2 days to deploy it. They need less than 2 days of a heads up to be able to get that site ready to drop in a microreactor and like turn it on and be ready to go because they need that resilient power fast. So all of those things considered, that's really what drove a lot of our early engineering decisions about how to make this product work for the customer that we needed. And I think that the takeaway from that for the industry is like it needs to be customer driven. We have a lot of really cool science projects that are happening this year, and we're going to be testing a lot of different technologies. But we need to make sure that the commercial demand is there for these to be able to scale successfully. Because if people are spending a lot of money on these technologies, they're going to want to make sure that they are getting the value that they need from it.
Yeah, I tell you, and actually, frankly, Phoebe, that was a great answer that provided, I think, sort of a great case basis for a lot of the things that we talk about. You know, the bringing as much let me back up and sort of you know, separate off large scale nuclear from the smaller nuclear, right? The large scale nuclear, much of it can't be done in a factory because the pieces are just too big. The assembly is going to happen, you know, on site, sort of necessarily. And so often when we talk about you know, nuclear supply chain and the challenges there, we're talking about large forgings, the reactor pressure vessels. We can get into some of the, you know, primary loop piping, you know, some things that require very large ingots and whatnot. And there's, I mean, worldwide, there's a small number of companies that produce those. Now, I think the opportunity in the US to stand up an industrial base to create, I'll call it smaller versions of some of those components. That is an opportunity, but it's an opportunity because much of that doesn't exist today. And where some of that manufacturing capability does exist, some of the vendors don't have what we call the N stamp. They don't have, they're not nuclear qualified to produce components for a nuclear power plant. Now, this is something else that I think Department of Energy and Nuclear Regulatory Commission leadership is working to get at, and we are supporting this in the National Laboratory System as well. The question being, does every part today that is required to be nuclear qualified, does it need to be, you know, nuclear qualified? Does every valve in the system or every pipe in the system have to have that N stamp? That's an interesting question, and frankly, I think there are opportunities to sort out what could simply be industrial grade, meeting certain stringent quality assurance requirements, but not necessarily what we call the nuclear quality assurance requirement. I think there's a lot of money that could be saved without compromising one iota on safety as we look at that. So growing the domestic industrial base, you know, in the US and for other countries that are looking to do that, I think those are some of the issues. And frankly, I think standing up the manufacturing capacity for some of the smaller components that small modular reactors and microreactors need. I think there's an easier line of sight from here to there than when I think about, you know, say pressure vessels for large scale nuclear. And so again, I think real opportunity to do what we can to grow the capacity, bring the assembly into the factory to the extent that we can. And what I always say, the big opportunity for SMRs, micros, is factory fabrication leads to cost and schedule predictability. Yes, I expect cost to drive down as well. But what I always say in nuclear, I talk to investors all the time that say, hey, look, I might be willing to get in the game, even on large scale nuclear, if I had a better sense that there were predictable schedules and costs. I'm willing to underwrite, you know, what can be sometimes a high cost to deploy, even though nuclear comes then with much lower cost for operations. What they want is schedule and cost predictability. That's what factory fabrication offers.
Amazing. So we've talked engineering, we've talked the supply chains, and we've talked markets now. Could you really quickly touch on the workforce and the operator staffing models and how these types of development investments in workforce will need to happen, need to change, whether that is at the SMRs, microreactors themselves, or along the supply chain as the industry scales in the near future?
Sure, maybe I'll start and offer a couple thoughts. I know Phoebe and the Radiant team is thinking a lot about this, and so I'm excited to hear that perspective. You know, what I like to remind people when we start talking workforce, I think when the nuclear industry starts talking workforce, it's easy for you know, external audiences to assume we're talking about droves of nuclear engineers. And frankly, that's not what I'm talking about. If we had droves of nuclear engineers flooding the market, we might get nothing done. And I say that lovingly. But what we're talking about is people who know how to put things in the earth and raise, structures, build things, get their hands dirty, weld pieces together. That's the workforce that we're going to need to enable the ambition that I laid out on one of those early slides I put up for, quadrupling nuclear energy in the US. That's going to take people who know how to build things. I mentioned my nuclear Navy background, and frankly, we were working through this several years ago, more than several years ago, as we were looking to increase the rate at which we could build nuclear powered submarines in our shipyards. There's only two shipyards in the US that build nuclear powered submarines. And getting more of that work done out of those two shipyards required a substantial investment in workforce deployment. But it wasn't a bunch of engineers. It was welders and pipe fitters and cable pullers and people who know how to build ships. And we got at that challenge. Well, that's where we are today in commercial nuclear. And getting out there and going back to Alicia's comment, everyone in this discussion is an ambassador for nuclear. And I think finding ways to engage nationally, regionally, and locally with the trade schools, with the community colleges, with those institutions that can say, hey, look, not everyone wants to go to college and get a college degree, but if you want a good paying job and you want to contribute to the energy security of where you live, and the economic development of where you live, good news. Nuclear offers a chance. Maybe it is working in a factory, assembling these reactors and pushing them off the assembly line. Maybe it's working in the field to actually deploy these things as part of an integrated construction project. With the AI and data center industry, they're looking at that same thing as well. And so, frankly, there's something of a competition for talent, but I think there's also a lot of synergy that we can all help each other and grow that workforce we need to scale.
I agree with Brian's comments 100%. It is the technicians, trades, welders. Those are the folks that we are going to be hiring in droves to actually be building our reactors. Um, One thing I'll mention is something I find super fascinating about the workforce challenge in the US too, is like the geography of it. Because right now we've got a couple of nuclear hubs around the US, but like they're pretty concentrated. And that is one of the reasons that brought Radiant to Oak Ridge, for example, because you have that really high nuclear IQ, you've got workforce there, you've got educational institutions that are there and ready to, step up and help fill those gaps. At the same time, a lot of other folks in the nuclear industry are also moving to these areas, and we are definitely going to be facing stiff competition as we're hiring in Oak Ridge and across the country. So making sure that Radiant can compete with other folks in the nuclear industry for a small pool of talent, will certainly be a challenge. That said, we're already getting so many people who are also approaching us saying okay, what can we do about workforce development? I know that American Nuclear Society does a lot of engagement on, K through 12 education. And you're also seeing a huge shift in young people, myself included, who come from clean energy backgrounds, and are finding new reasons to get involved in the nuclear industry. They have new motivations for wanting to see this technology succeed. And I think that speaks to, both the decades of, people are realizing, we've had nuclear power plants operating for years, providing clean energy, operating very safely. So they see that history. But then you also have, this newer momentum that's very exciting for folks who maybe were not in the nuclear industry before and are now seeing this enthusiasm and saying yeah, I want to be a part of that. So that's really great to see both from the inside, but also seeing other folks, just in my network who are not from nuclear industries and, becoming more interested in these issues. Um, but all that said, we've got big challenges ahead of us, but I think we know where we need to be, and we're starting to put those plans together to make sure that we have the people that can support this. For both, these hubs like Oak Ridge, like Idaho, where you need a lot of people in one location, but also as we're deploying SMRs all over the country, we'll have these like very distributed resources now. So how do we manage different microreactors that, may not be in the same place? If there's just one microreactor, in one state, and another microreactor, 100 miles away, can we leverage the same people to be operating both of those facilities? And then the last thing I'll mention, I think that is really interesting on this, is the recent DOE RFI on nuclear life cycles, the fuel life cycle. And you saw a lot more states than have historically been involved in nuclear raising their hands and saying, yes, we want to be a part of this process. So I think, as the economic opportunity from the nuclear industry can expand across the US and, invite new communities and new states to be, to have a part of this prosperity that we'll see as the nuclear industry continues to grow. I'm very excited to see how that will benefit, communities and economic development across the board.
Amazing. Thank you. Oh, Brian, go for it. You
No,
want to
I'm
jump in?
sorry, Max. One other thing. Phoebe, great call out to the Nuclear Life Cycle Innovation Campuses or NLICs. That is an exciting kind of new development that the Department of Energy was leading. And folks can go online and learn more about how that is intended to kind of get at this fuel piece that we talk about. But one other thing, Max, in your question, you also brought up kind of the deployment models, especially for a lot of these smaller reactor technologies, and that is also when we think about use cases and deployment models, kind of a cool new horizon for advanced nuclear, where and take the Radiant design for example, and what Phoebe was showing in terms of a footprint. Well, perhaps not surprisingly, these deployment models, especially for so many of these smaller reactor designs, it's not the same as what you have for today, the large scale nuclear reactors, that require hundreds or thousands of workers working in shifts, 24 hours a day, monitoring the plant and managing safety and whatnot. With these smaller designs that come with some of these inherent and passive safety features, perhaps not surprisingly, as part of that evolving regulatory framework, the NRC is considering exactly that. What about a developer that wants to deploy thousands of these reactors across the geographic space and monitor them from a safety and security standpoint from a control center? That would seem feasible. It is obviously going to have to be looked at through the regulator lens. But that's exactly what the NRC is doing, and so that is a very cool, exciting frontier in the deployment model for these reactor technologies.
Wonderful. Okay, we're running short on time, so as parting thoughts, I would love to invite you both, as well as Alicia, if you would like to provide what is your one key takeaway you would like the audience here or anybody watching the webinar to take away from what we've discussed today. So maybe we can start with Brian, then Phoebe, and then Alicia, we can end with you if you'd like to.
Oh boy! All right, I'm gonna have to go in front of Alicia. I don't know that I feel comfortable, but I'll try. I guess all I'll say is maybe to come back to the folks who joined this webinar. It's not like it's a bunch of nuclear engineers, but it is everybody involved in nuclear. And so this is an all hands on deck, all of the above effort that requires the support and the messaging from everybody. And that to me presents an exciting opportunity. Again, I often say our biggest ambitions in nuclear, it's not a physics problem, it's not an engineering challenge. We're talking economic models for an exciting type of technology that truly can, lift countries up, lift regions up, lift localities up in terms of human potential and economic development. So I just love to see the cross section of folks engaged in this discussion, and I just want to reiterate how honored I am to be a part of it.
Move on to Phoebe. Thank you so much for that.
Yeah, agreed. I'm happy Alicia's going last. I've had the pleasure of seeing her speak a number of times, and she always has the most inspiring words taking a technical conference, and making it about, leadership and growth and what you can do as an individual. I always appreciate those comments. Um, I'd say my main takeaway, I think, would be the comments that I made on timeline. Our moment is here and like things are arriving faster than we think. And I think, it's always a challenge of like industry asking government, come on, we're moving faster, catch up. But I think not just at the federal level, but at the state level too, as we're looking forward to commercialization of these technologies, we still have a lot of gaps from supply chain, from workforce, but also looking at, some of these novel technologies like microreactors, is if folks are involved, at the community level, the local level, the state level, we're also going to need to figure out how we're going to be permitting these at like the locality, at like the local level, at the state level too. And a lot of states don't even know what their definition of microreactor is yet. That's something that like we're starting to work on. But no, it's just one company with 50 states who are potentially interested in nuclear power. It's a lot to take on. But as you're having conversations around policy, think about, what can we do in the near term, but also how can we enable scaling in the long term? And those are really like the two things that we are trying to balance, especially as a startup too, is, make sure we can deploy Dome and be as successful as we can in 2026, but making sure that we are ready to be deploying 50 reactors a year by 2030. So we're dealing with a lot of very exciting challenges. And yeah, again, happy to be a part of this movement. So thrilled to have been a part of this webinar. Thank you so much for everyone for hosting and attending.
Thank you so much, and thank you for speaking and joining us today. And then we'll move on to Alicia to wrap us up.
Well, thank you. And I thank you, Brian and Phoebe, for hyping up what will surely be disappointing. But I appreciate the confidence that you have in me. So first of all, let me thank you both for being here. One of the things that I really appreciate, Phoebe, and I was texting Rita during this webinar, one of the things I really appreciate is that we have young people so active in our plans to deploy. And this needs to be a global push that we include our young people early and often. And I would say it's never too young to start. There are states in the United States that work with 6-year-olds and do science on Saturdays. We really need to encourage our young girls and boys that STEM is for them, that there are careers for everyone in nuclear, that you don't need to be a nuclear engineer. In fact, at a site, there's probably less than 20% nuclear engineers. I think that percentage might even be a bit lower. There's a career in nuclear for everyone. And so when we think about the technology and the advances that you've heard today, recognize that the technology is happening. We're not talking about the future. We will see technology critical in the United States on July 4th. So what that means is we need to make sure that along with these projects, we are very focused on the people. That you should consider part of your number one job, to make sure that your country is very people focused and training the workforce and developing leaders and making sure that we're looking across populations for young boys and girls to be part of this growing ecosystem. It will take all of us. I'm glad you joined us today. I thank Max, Jal, and Holly for their efforts, and Anusha, and I look forward to seeing you all at our next webinar. Max, over to you.
Thank you so much for those wonderful words. So with that, thank you again, everyone, for joining today's session. The Nice Future Initiative, the only nuclear initiative of the SEM, is proud to support knowledge sharing on nuclear topics such as these. If you're interested in participating in Nice Future Initiative activities, please go to our webpage, shown here, and in the chat as well. Thank you again for our speakers. Everybody has been absolutely wonderful today with their presentations and their discussions. We look forward to seeing you all in the future. Thank you so much again.